Not only God knows. I know. And by the end of the semester, you will know. This is how the physicist Sidney Coleman would kick off his lectures on quantum theory at Harvard. Coleman claimed that he never really liked teaching, but his enthusiasm was electric, and his courses were considered legendary. Though his name is not as well known as Einstein or Hawking, he was held in the highest regard amongst his peers. Indeed, groundbreaking physicist Sheldon Glashow once said, "He's kind of a major god. He is the physicist's physicist." And yet, arguably, this jovial legend of physics' greatest achievement was revealing something truly spine-chilling. For in the late 1970s, Coleman figured out how to destroy the entire universe. The possibility that we are living in a false vacuum has never been a cheering one to contemplate. However, one could always draw stoic comfort from the possibility that perhaps in the course of time the new vacuum would sustain, if not life as we know it, at least some structures capable of knowing joy. This possibility has now been eliminated. Coleman discovered that our universe is under constant threat, that at any moment, at any point in time and space, reality could begin to change. Change in a way so unforgiving that nothing could survive it. The story of the unraveling of this mystery will introduce us to some of science's great personalities, men and women who peeled back reality and created a framework out of which our universe could appear. But most importantly of all, this story will pull us deep into the bizarre world of the standard model of particle physics, and the one particle that sits apart from all the others. The one particle with the power to eliminate everything in existence. That goddamn particle, or as it's more commonly known, the God particle. The Soviet Lunokhod rovers explored the moon in the 1970s, remotely driven from mission control in Crimea. Operators viewed live TV images sent from the lunar surface and radioed commands back via their landers, a true feat of engineering for the time. Indeed, it wouldn't be until 1997 that another remote control vehicle would land off-world. Sometimes it's useful to be able to control something remotely, even from the other side of the world. And if you're looking to remotely control your computer for personal or business reasons, AnyDesk can help. AnyDesk is a lightning-fast remote access tool that makes it feel as if you're sitting right in front of the remote machine. Indeed, we find it especially useful for video editing. Our editors can access their high-performance desktops back at home on the go, even with low-spec laptops. This allows us to take cheaper, older, or more portable machines to the coffee shop or gym without losing any productivity. AnyDesk is available across all major platforms, is backwards compatible with older operating systems, and has 99.98% uptime reliability, so you can depend on being able to use it when you need to. And what's more, personal use is totally free, with tailored plans for team and business environments. So head to anydesk.com to try this premium remote access tool free of charge. As the Trinity test mushroom cloud bloomed into the sky on July 16, 1945, physicist Kenneth Bainbridge turned to Robert Oppenheimer and uttered the immortal phrase, "Now we're all sons of bitches." Indeed, after the magnitude of the test had set in and the initial flurry of excitement had dulled down, there was a palpable sense of unease across many at Los Alamos. In the initial rush of adrenaline after the detonation, famed New York physicist Richard Feynman had played his iconic bongos on the hood of a Jeep, and in his words, everyone had parties. But quickly, the mood would turn sour. I sat in a restaurant in New York, and I looked out at the buildings, and I began to think about how much the radius of the Hiroshima bomb damage was and so forth. And I would go along and see people building a bridge, or they'd be making a new road, and I thought, they're crazy, they just don't understand. Why are they making new things? It's so useless. The Manhattan Project had employed over 130,000 people in its prime, and 26 of its scientists already had or would go on to win a Nobel Prize. It had been the focal point for much of the physics community for half a decade. And so after this long interruption, it was decided that physicists should gather together to return to science for science's sake once again. And in 1947, Oppenheimer himself helped organize a conference on Shelter Island. To quote later Nobel Prize winner Julian Schwinger, it was the first time that people who had all this physics pent up in them for 5 years could talk to each other without somebody peering over their shoulders and saying, "Is this cleared?" And it would be at this conference that Richard Feynman and Julian Schwinger himself would propose some groundbreaking quantum ideas. But what does any of this have to do with Sidney Coleman and the destruction of the entire universe? To answer this question, we must take a journey downwards, down into the deepest layers of reality. Down below the scales of molecules and atoms, beyond the pieces of the atomic nucleus, down to what we think are the ultimate building blocks of reality. And to a physicist, this world is written in the language of the Standard Model of particle physics. The Standard Model is the result of more than a century of deciphering the laws of the universe, a world even more fundamental than the atomic one explored by the Manhattan Project. First, there are the fermions, the fundamental particles that comprise the stuff of matter. Named after Italian-American physicist Enrico Fermi, fermions come in two types, the quarks and the leptons, that feel the fundamental forces differently. The quarks feel the strong force and are bound together by it into composite particles, collections of 2 or 3. Indeed, these include the protons and neutrons that sit at the core of every one of your atoms. Atoms that are circled by electrons, which, as leptons, completely ignore the strong force. And the complement to the fermions are the bosons, named after the Indian physicist Shachendranath Bose. The bosons are different, as they carry the fundamental forces between the fermions. For the strong force we met a moment ago, the carrier of force is the gluon. For electromagnetism, the boson is the photon, the particle of light. For the weak force, there are the W and Z bosons, and for the final fundamental force, gravity, physicists still aren't sure. Now, the idea of bosons as force carriers may seem strange, but you have to remember that particles are not really particles. And this is key. The Standard Model is written in the language of quantum mechanics, where everything is a wave in a field. An electron is a ripple in the electron quantum field. A quark is a ripple in a quark quantum field, and each boson is a ripple in a boson field. Everything is fields. In the simplest form, a field is something that is spread throughout space, and that something attaches a number to each point in that space. For example, think about the temperature in the air around you. Some spots may be warmer, some cooler, and at each point, the temperature is represented by a single number. This is a simple scalar field. Other types of fields are more complex, but still familiar. For example, electric and magnetic fields. At each point in space, the electric and magnetic fields have a number, and, importantly, a direction. And so, with a vector at each point in space, it is no surprise that these are known as vector fields. And these, and many more complex fields, are what many aspects of physics are built from. In particular, a type of field called a quantum field. And to explore how these work, let's talk about the electron. The electron quantum field fills all of space, encoding the properties of what makes up an electron at every point. A single ripple in the field corresponds to a single electron traveling through a region. Multiple ripples would represent multiple electrons, all encoded in the field. And of course, when the field is zero, there are no electrons in that region. The electron field is joined by fields for the other leptons, the muon and the tauon, and their associated neutrinos. There are also fields for each of the quarks and for each of the force-carrying bosons. There is a quantum field for each type of fundamental particle. All around us, at every point, sit all of these quantum fields. But there's more to quantum fields than simply existing. The real power in quantum fields is how they interact. Understanding just how this interaction takes place was one of the most important insights in all of physics. And it is here we can return to Shelter Island and Richard Feynman. As part of his PhD, Feynman had realized he could bring a mathematical shortcut to quantum calculations. Let's look at what happens when two electrons with their negative charge approach each other. To begin with, it's important to remember that the two electrons are ripples in the electron quantum field, so they are not feeling each other's presence through their individual electric and magnetic fields. Instead, the presence of the two electrons in the electron field generates a new ripple, and this ripple is in the photon quantum field. And the photon is the boson of the electromagnetic force. This photon ripple travels from one electron to the other, and in doing so, it transfers energy and momentum from one electron to the other. This transfer of energy and momentum is precisely why the photon is known as a force particle. And when you look at a lonely star on a dark, dark night, the absorption of a photon on the retina in your eye receives energy and momentum from that star. Energy and momentum that was released by an electron in its distant atmosphere. And so, at the Shelter Island Conference, physicists were coming to grips with this quantum picture of electrons and photons. Julian Schwinger, with his crisp and refined New York accent, lectured first. He was followed by Feynman and his Queen's drawl, who made his way to the blackboard. Feynman's talk was shorter and shallower than Schwinger's, with lots of concepts and ideas. But with his tricks and famous Feynman diagrams, he showed he could shortcut Schwinger's mathematics. Other physicists were initially confused, but in the long run, his ideas won out. And he shared the Nobel Prize with Schwinger in 1965 for their insights into how quantum fields interact, with Japanese physicist Shinichiro Tomonaga also grabbing 1/3 of the prize. He had delved into the nature of quantum fields whilst isolated in his war-torn country in the 1940s, on the other side of the conflict to Feynman and the Manhattan Project. And so by the time of Feynman's Nobel Prize win, the Standard Model was growing in success. There were still theoretical holes that needed to be patched, but things seemed to be fitting together nicely. All forces should be written in the same quantum language, with bosons transmitting forces between fermions. All of these requiring the presence of quantum fields to carry the particles, with particular numbers, the charges of the force, dictating how strong the interaction is. Except, a major mystery remained. A mystery that had the potential to tear it all down. For within the Standard Model, all of the fundamental particles seemed to have absolutely no mass. The particle of light, the photon, appeared to be massless. That was true, but not the other particles. Clearly, not even the electron. And so to understand this mystery, we have to talk about one more fundamental force, the weak force. The existence of quantum fields demanded that there was the equivalent of electric charge for the other fundamental forces as well. The strong force, for example, had 3 types of color charge, known as red, green, and blue, charges that determined how gluons are exchanged and how the strength of the strong force operates. But for our story, it would be the charge of the weak force that would play a pivotal role. The weak force, unsurprisingly, is weaker than the strong force and electromagnetism, but it is still stronger than the pull of gravity. But unlike the other forces, the weak force can flip the identities of quarks and leptons through the exchange of bosons, and this means it is responsible for certain types of radioactivity. Of course, with Feynman's view of quantum interactions and the need for bosons to transmit fundamental forces, there was a need for a boson to transmit the influence of the weak force. But one of the complicating features of the weak force is that there are 3 force bosons that can be exchanged. These are the Z0, the W+, and the W-. The plus and minus here signifying that the W boson carries its own electric charge. And as well as this, unlike the other force bosons, the photons and gluons, the W and Z bosons have mass. Lots and lots of mass. Indeed, each W and Z boson is about 80 times as massive as a proton or neutron. And it is this immense mass that severely impacts the influence of the weak force. While massless particles and gluons mean that electromagnetism and the strong force have infinite range, the W and Z mass ensures that the weak force can only operate over less than 1/millionth of a billionth of a meter. This is a result of Heisenberg's uncertainty principle, one of the central pieces of quantum theories. The energy for such a high mass must be conjured out of nothing. But because of that high mass, the amount of energy can only be borrowed for an extremely small amount of time. The amount of energy borrowed from the vacuum inversely related to the amount of time it can be borrowed for, and in this short time, the boson can only move an extremely small distance before it decays into other particles. And so, we have said that the weak force is important, and we have found that its force bosons are massive. But still, the question of where this mass comes from has yet to be answered, or indeed, what this has to do with the possible end of the universe. It is time, therefore, to dive even deeper into the physics of the fundamental. And to do that, we will need to find a man who does not want to be found. Dr. Higgs, the J.D. Salinger of physics, has already let it be known that he will not be available in any form on Tuesday. On the morning of October the 8th, 2013, the world awaited the announcement of the Nobel Prize in Physics. Peter Higgs, however, wanted no part of the expected media frenzy. Indeed, instead of staying at home to receive the expected calls and interviews, he quietly slipped away to a local pub. But as the hours ticked by and Higgs dined on soup and trout, the media frenzy in the outside world was building, and Higgs could not hide forever and headed out of the pub later in the afternoon. He bumped into an old neighbour on the street who immediately congratulated him on the good news. "What news?" Higgs asked. Yet there could be no doubting what the news could be. He would be going to Stockholm. But why had he been selected for this coveted prize, one received by Feynman all those years before? To understand that, we will have to return to another Nobel ceremony, one perched between Higgs in 2013 and Feynman in 1965. Nobel Award ceremonies have always been flashy affairs, with pomp and regimented protocol. And indeed, the 1979 award was no different, with the royal family of Sweden leading the processions and celebrations. All the men were dressed in formal dinnerwear, stiff black suits and white ties. Well, almost all. One man in distinctly different clothing and a turban stood out. The man was Abdus Salam, only the second Nobel Prize winner from a Muslim country. And unlike Egypt's Anwar Sadat, who had collected the prize for peace the previous year, Salam was in Stockholm to receive the Nobel Prize in Physics, and his choice of dress reflected his pride in his religion and cultural origin. Let us strive to provide equal opportunities to all so that they can engage in the creation of physics and science for the benefit of all mankind. Although he was not alone, as Sheldon Glashow and Steven Weinberg would be sharing 1/3 of the prize each, and they were all there for the same reason. These 3 physicists had delved into the similarities between electromagnetism and the weak force, today known as electroweak theory, and this unification of the two laid the groundwork for understanding the origin of mass. But before we explore the electroweak and its consequences, we have to remember that electromagnetism itself used to be two separate things. Electricity and magnetism used to be two very different and distinct phenomena. It was in the latter half of the 19th century that the Scotsman James Clerk Maxwell wrote the equations that unified the two. Maxwell, following work by Michael Faraday, noticed a symmetry, the echo of one field birthing another in elegant reciprocity. He also added a single term to make the equations whole, and in doing so, unleashed light. Light, he realized, wasn't separate either, simply a wave of the unified electromagnetic field rippling through space. This was the first great unification, not born of speculation but of mathematics, compelled by beauty and truth. It was hugely important, as it sparked an idea that still drives physics forward today. For if things as different as electricity and magnetism could be shown as different aspects of one underlying theory, then maybe other, seemingly disparate aspects of physics could be unified together. And so scientists did what scientists do. They kept questioning. What if all of physics could be encompassed in a single set of unified mathematics? What if all of physics could be bound together into a single theory of everything? The race was on. The first clue was that some of the bosons of the weak force carried electromagnetic charge, meaning that those bosons could intrude on the electromagnetic world, interacting with the photon quantum field. And this gave Glashow, Weinberg and Salam the key to a second unification, that of electromagnetism and the weak force. But to understand how electroweak theory unites the two, we must take a deeper look into a complex idea within physics. We need to look at gauge theories. A gauge theory takes its name from the word gauge, a kind of measuring tool or standard. It's about setting a local reference, like choosing a map's grid at every point on the land. Shifting those local references only changes the description, not the underlying landscape itself. So, gauge theories reveal laws of nature that stay constant, no matter how you adjust your view. Physicists treasure these symmetries, the scientific term for something that stays the same even when you transform it. They hint at hidden structures in the universe. And so let's consider a simple kind of gauge field, a field represented by a single value at every point. This value is an angle between 0 and 360 degrees, so it tells you, locally, what direction a small arrow, a vector, is pointing. But, and this is key, every single one of these vectors has exactly the same length. If your laws of physics care only about the length of the vector, not its direction, you have a gauge symmetry. You could change the direction of every single vector throughout the space, but as long as the length remains the same, your physics would, too. And from this quiet, circular idea, we can build the foundations of forces. For from symmetry, deep laws of nature begin to emerge. This might sound abstract and have little to do with the real world, but in their simplest forms, quantum fields are similar. Quantum fields are built of complex numbers, so that two numbers are encoded at each point, with the modulus of the complex number, the sum of the squares, the important element. Because it is this quantity that corresponds to the probability of finding a particle at a particular location. This means that we can rotate our complex numbers in the same way as the example we explored earlier, meaning that quantum fields also possess a gauge symmetry. We can change the field and leave the physics intact. And the person who kicked off this focus on symmetry was Emmy Noether. Born in Erlangen in 1882, Noether faced the heavy doors of academia. A woman in a man's world, her mathematical brilliance was often left unspoken, although not by her esteemed colleague, Albert Einstein. In the judgment of the most competent living mathematicians, Fraulein Noether was the most significant mathematical genius thus far produced since the higher education of women began. And quietly and rigorously, she laid the path to a universe built on elegant symmetry. For what Noether discovered was not mere mathematical curiosity. She saw that hidden symmetries whispered deep truth about physical law. That if a system stays the same when it is changed, something has to be conserved. And suddenly, the conservation of energy, the idea that energy could not be created or destroyed, just transferred, was no longer just an assumption. It was a theorem. Things quickly got a lot deeper than this, for Noether's insight was profound. A shift in time, energy must remain. A step to the side, momentum preserved. With this, symmetry moved from mere elegance to the engine room of the cosmos. The symmetry we mentioned before, to do with vectors and rotation, goes by the name of U1. And as it turned out, this is the symmetry that is the mathematical foundation of the electromagnetic force. Technically, it's related to the phase of the complex numbers of the electron quantum field, and the conserved quantity in the case of electromagnetism is electric charge. However, the U1 symmetry that defines electromagnetism was too simple to account for the weak force. So, the question became, just what gauge field and symmetry would work? And it was wondering about this that brought Glashow, Weinberg and Salam to Stockholm and their Nobel Prize. They realized that two additional quantum numbers, known as weak isospin and weak hypercharge, were needed. And just like the electric charge defined the electromagnetic interaction, these defined the weak interaction, and that a more complex symmetry group, known as SU2, was needed. Like U1, the SU2 symmetry group is a way of describing certain kinds of rotations, but instead of dealing with regular space, it applies to a more abstract kind of space used for quantum fields. Instead of the simple circle-like rotations of U1, we have to imagine a sphere where every point represents a possible state of a quantum particle. SU2 describes how these states can smoothly rotate into each other while keeping the overall structure intact, the sphere. It is difficult to visualize, but no one said that quantum field theory was easy. And so by combining the U1 symmetry of electromagnetism with SU2 of the weak force, the Nobel Prize winners had shown that these disparate phenomena were two sides of the same coin. And the mathematics predicted the presence of 4 force-carrying bosons, called B, W1, W2, and W3. Problem solved? Not quite. To quote Steven Weinberg, one of the consequences of the electroweak symmetry is that if nothing new is added to the theory, all elementary particles, including electrons and quarks, would be massless, which, of course, they're not. And so the quest continued, with the answer lingering in the fizzing chaos of the Big Bang. Just after the universe was born, it was extremely hot, and this meant that all particles were zipping around at almost the speed of light. That amount of energy in the mass of any particle would be negligible compared to its energy of motion, effectively like a particle of light with no mass at all. And what this meant is that in the earliest instance of the cosmos, there were not two distinct forces, no separate electromagnetic and weak. There was only the single electroweak force operating. And so something must have happened as the universe expanded and cooled and split this into two. Something must have happened to tear apart this perfect picture and split electromagnetism from weak. Something must have happened to give mass to the bosons of the weak force. Something called symmetry breaking. And this is where in 1964, Peter Higgs and his fellow physicists took the stage. Although Higgs himself, ever keen to shun the spotlight, wasn't sure of his suggestion. "This summer, I have discovered something useless," he wrote to a colleague that year about his Nobel Prize-winning idea. The answer, he and others realized, was in the addition of another quantum field. A simple quantum field that just had a single number at every point. A scalar field. This quantum field, however, had to have quite different properties to other quantum fields, and it all came down to what it means for a quantum field to empty. To understand this, let's go back 13.8 billion years, to roughly 1 picosecond after the Big Bang. In this hot, energetic state, all of the quantum fields of the universe buzzed with energy, with all of this energy whooshing back and forth between the various fields. But this superhot universe was only temporary, as it expanded and cooled. And so the flow of energy began to dwindle, meaning the buzz in the quantum fields also started to die away. Eventually, the cooling resulted in the fields losing all of their buzz, becoming zero except for the odd ripple here or there representing a particle passing through. But for the Higgs field, as it is now known, things were very different. In the early universe, the Higgs field buzzed and fizzed, interacting with the other quantum fields. And, as with the other fields, as the cosmos cooled, the buzz in the Higgs field also died away. But, unlike the other quantum fields, the buzz in the Higgs field never completely vanished. At some point in the cosmic cooling, the Higgs field got hung up, such that the Higgs field possessed a value which was non-zero at every point in space. But why? What made the Higgs field different? Why didn't the Higgs field eventually fade to zero? We can think about a typical quantum field as being like a pendulum. In the early universe, with lots of energy, the pendulum swings wildly from side to side. For the quantum field, this amplitude represents the values over the field. But as the universe expands and cools, the amplitude of the swings gets smaller and smaller. Eventually, all the energy dissipates and the pendulum comes to rest, hanging straight down with swings of zero amplitude. Effectively, the quantum field vanishes all over space. However, for the Higgs field, as the universe cooled, it didn't settle down like a pendulum. Instead, due to its particular properties, it became like a pencil balancing on its very tip, with the rest of the universe cooling around it, its balance becoming ever more precarious. And yet despite its precarious position, in this balanced state, the Higgs field was zero everywhere. But it couldn't last. Whilst the Higgs field was balanced like a pencil, the electroweak bosons remained completely massless. But just as a pencil falls and drops to a lower potential energy, the Higgs field dropped as the energy fell, finally taking on a non-zero value everywhere. And so just as a balanced pencil is symmetric, looking the same as you walk around it, with a fallen pencil, that symmetry is lost. The result of this symmetry break for the electroweak force was profound. The bosons predicted in the theory, B, W1, W2 and W3, quantumly mixed together and formed 4 new bosons. One of them remained massless and is the photon of the electromagnetic force, and the other 3 gained mass from the breaking, becoming the weak force Z0, W+, and W-. We can now take a deep breath. We have found the origin of mass of the fundamental boson of the weak force. But what about the masses of the other fundamental particles? Where do they come from? The answer lies in the fact that after symmetry breaking, the Higgs field is non-zero everywhere. And it is this fact that could also hold the key to the end of the universe. The Higgs field is a relatively simple quantum field, characterized by a single number. This number is known as the vacuum expectation value, or VEV for short. And, basically, every particle's mass depends on how strongly it interacts with the Higgs field. But just how does the Higgs field confer mass on these fundamental particles? To understand this, it is important to understand what mass is. You might think mass is simply the amount of stuff that comprises something, or maybe mass is the thing that produces the force of gravity. But the important definition is the one that was given to us by Newton's second law of motion, more than 400 years ago. Force is equal to mass times acceleration. Mass is the way an object responds to a push. Because of this form of mass is known as inertial mass, and it is the reason why moving an elephant is much harder than moving a mouse. It is the Higgs field that gives particles their inertial mass, making them harder to push, and it does this by effectively making space sticky for particles that can interact with it. For the massless photon, for example, the Higgs field is effectively transparent, and so it moves at the speed of light. But the electron and other massive particles feel its sticky presence. And it really is that simple. And so, there it is. It may seem that we have come to the end of the journey in understanding the origin of mass. But there's still a couple of questions that remain to be answered. Because the mass of the fundamental particles, especially the electron and the up and down quarks, the particles that make up matter, are very, very small. If we consider a proton, which is comprised of two up quarks and a down quark, the masses of these three fundamental quarks make up only 1% of the mass of the sum total. And so, where does the rest of the mass come from? What is the origin of all the rest of the mass that makes up you? We have to remember that inside each proton and neutron there's a lot more than just the three quarks. Inside each and every one of these particles, there is a swirling mass driven by the strong force. A hail of gluons is constantly being exchanged between the quarks, and these gluons are popping in and out of existence as quark-antiquark pairs. Whilst the gluons themselves are intrinsically massless, they still carry a swirl of energy and momentum, and through Einstein's E=mc², this swirl of energy corresponds to mass. It is this that gives the particles of matter at the center of your atoms most of their mass. Just think about that the next time you find it difficult to heave yourself off the sofa. And so, there was a time when the universe was 1,000th of a billionth of a second old, when the temperature of the cosmos was 1,000,000 billion Kelvin, that a defining symmetry was irrevocably broken, and the cosmos was imbued with mass. But again, what does this have to do with the destruction of the universe? To answer this, we will have to do something that seems counterintuitive after all we have learned so far. We will have to weigh the source of mass, the Higgs itself. Sidney was both an incomparable teacher and the sharpest critic in the world of theoretical physics. He was Pauli's tongue in Einstein's image. We have been deprived all too soon of one of our generation's most profound and imaginative minds. Sidney Coleman died in 2007 after a long illness, to an outpouring of affection from many in the physics community. His obituary in the Harvard Gazette proclaimed that almost everyone had a Sidney story, his caustic wit and legendary lectures almost universally loved. But it would be 5 years after his death in 2012 that other physicists would finally start to answer a mystery he had uncovered years before, with the help of the most energetic experiment ever performed. In the late 1970s, Coleman had looked again at the symmetry breaking that led to the Higgs field fizzing with constant energy, in turn giving mass to fundamental particles. And he asked, why? Why did the Higgs field fizz with the particular energy it has? Why didn't the Higgs field settle on a different energy as the universe cooled after its birth? In the initial work of Peter Higgs and others, they had simply assumed the energy of the Higgs field. They didn't know what this energy must be. In their mathematics, the Higgs field just settled at this energy. But Coleman realized that with only a little mathematical manipulation, things could change. There might be more than one energy that the Higgs field could settle into. Indeed, due to the intrinsic randomness of symmetry breaking, it seemed to be nothing but a game of chance. Just like the pencil balancing on its tip could topple to the left or right, front or back, the path the Higgs field toppled from its symmetric state seemed equally random as it fell into an energy minimum. And it was here that Coleman realized something disturbing. This meant that after the birth of the universe, the energy in the Higgs field may not have fallen to a true minimum. Instead, it could be hung up in a local minimum, not a global minimum of the Higgs energy. But why should this be a problem? Surely, even if we are in a local minimum, it's clear that our universe happily exists and functions in this local minimum. Well, the issue is that quantum fields are quantum. Remember our picture of a quantum field like a ball rolling about a landscape. In the simplest picture, the ball ends sitting at the very bottom of the valley. In the simplest Higgs field, this picture of the valley remains, the ball still making its way down to the lowest point. However, in the more complex landscape envisioned by Coleman, the ball can be trapped, stuck in a dip in the peaks, but still a very long way above the valley floor. Of course, in the classical picture of the universe provided by Isaac Newton, this is no problem. The ball would be forever stuck in this divot. But quantum mechanics offers the ball an escape. For within the mathematics of quantum mechanics, there is something called tunneling. Quantum tunneling is something not seen in the mathematics of Newton, as things in quantum mechanics are represented as waves and are never truly localized. As we've seen before, quantum waves, like waves on the ocean, spread out through space and time. And so quantum waves can leak between seemingly distinct and separated regions of space. Imagine an electron locked in a high-security prison cell. A Newtonian electron would be stuck in the cell forever, bouncing back and forth off the wall. But the wave function of a quantum electron, whilst initially confined to the cell, will spread beyond its walls and bars. The existence of the wave function beyond the walls of the cell gives the electron a chance to escape, a non-zero probability that the electron will be found outside the cell. This ability to quantum tunnel is extremely important for the workings of the universe, as it provides a vital pathway for things as varied as the sun shining and electricity flowing into your phone. But quantum fields can also make use of this quantum tunneling, allowing them to transition from one state to another. And so this means, if the Higgs field is stuck within a local minimum, there is a probability that it can transition to a lower energy. But what would this mean? Surely it's just the presence of the Higgs field that's important. So it's still there, fundamental particles will still have mass, and the universe would be more or less the same. But this is not the case. For transitioning to a lower vacuum energy has a drastic effect. It floods the cosmos with energy, completely destroying the universe as we know it. To quote Sidney Coleman, by macrophysical standards, once the bubble materializes, it begins to expand almost instantly with almost the velocity of light. As a consequence of this rapid expansion, if a bubble were expanding towards us at this moment, we would have essentially no warning of its approach until its arrival. This quantum tunneling of the Higgs field would occur at a particular point in space, at a particular point in time, and would roar away at the speed of light, incinerating everything in its path. And within this expanding bubble, a strange new universe would remain. A universe very unlike the one we inhabit today. This is because the lower Higgs state within the bubble would change not only the masses of the fundamental particles, but the action of the fundamental forces. This would change everything, including the ultimate stability of matter. There could be the prospect of no atoms, no stars, and no planets. Not only that, but the roaring turmoil inside the expanding bubble could be even more dramatic, and it might influence the very structure of space and time themselves. Within the bubble, the expansion of space might completely cease, and instead, whatever is inside the bubble could undergo complete gravitational collapse. And so, how worried should we be? Is the decay of the Higgs field a realistic possibility for the cosmos? Or could our universe be sitting at the true minimum of the Higgs field, so there's nothing to worry about? Physicists aren't completely sure on the answer to this question, but there is one incredibly powerful recent experiment that has given glimpses of an answer. Nestled in the coal mining valleys of South Wales lies the small community of Combach. It was here that Lynn Evans was born in the mid-1940s. As a young boy, he found his love for science, originally studying chemistry at the University of Swansea, before finally being drawn into the mysteries and magic of physics. This was a fortuitous move, as his studies led him to the subatomic world, and by the close of the 1960s, he found himself at CERN on the Swiss-French border. This small collection of buildings around a particle accelerator was still only a few decades old, but it was already the premier place to study the fundamental nature of reality on the smallest scales. Energy is the name of the game in particle smashing, accelerating beams of matter to almost the speed of light. Colliding the beams concentrates these immense energies into tiny volumes, and through the wizardry of Einstein's E=mc², this energy can be transmuted into new, massive particles. And so, of course, physicists worked on getting particles to go faster and faster. By 1989, the Large Electron-Positron Collider was constructed in a circular 27-kilometer tunnel, zipping electrons around at nearly the speed of light before smashing them into equally zippy positrons. But the physicists at CERN were thinking ahead to what would come next, a machine even more powerful. And the job was given to Lynn Evans to make it happen. Evans the Atom, as he was known, took on the role of project director at the Large Hadron Collider, upgrading the Large Electron-Positron Collider to accelerate protons instead of electrons. Being 2,000 times more massive than the electron, the proton could bring a lot more energy to the collisions. This project would take the effort of tens of thousands of scientists and billions of dollars, as well as a decade of construction under Lynn Evans' guiding hand. And despite hiccups and setbacks, in 2008, they were ready to turn on the proton beams and begin operations. Usually, the start of operations are quiet affairs, overseen by the scientists responsible for the beams and detectors. But the sheer power of the Large Hadron Collider had sparked conspiracy theories in the media and online. Some even claimed that mini black holes would be created, instantly destroying the Earth. And so even though he initially hadn't wanted to, Lynn Evans decided the launch of the LHC would be a public event. In front of the world's media, the LHC was brought up to speed. People around the world held their breaths, some willing everything to work properly, others afraid that the LHC would spell doom for the planet. But as Lynn narrated what was happening to the press, the room erupted into applause. The LHC was alive. The protons were circling at almost the speed of light, and the planet Earth was seemingly safe. At least, so it seemed at first. The energy of the LHC was steadily ramped up, and physicists started sifting through the outcomes of the collisions. All kinds of particles were created and spat out into the massive detectors, but some physicists were on the lookout for a particular pattern. And in the flood of collisions, they found it. a whisper of the Higgs, written in light itself. A decay path predicted decades before by Peter Higgs and many others, now etched in lines of data. And so to understand what happened, we're going to have to look a little more deeply into collisions between protons and antiprotons. To begin with, we have to remember that protons are not fundamental, but are constructed from smaller particles. Inside a proton is a broiling mess of quarks, and as well as quarks, gluons zipping back and forth, carrying the action of the strong force and binding the proton together. It is the collision between pairs of gluons that is the source of Higgs boson production, combining to create a buzzing mixture of top quarks, the heaviest of the quarks. It is this mix of top quark that has enough energy to condense into a Higgs boson, a brand new ripple in the Higgs quantum field. This Higgs boson can decay through various different ways, through Z bosons, quarks and photons, decays that cascade through other decays. And it is these that were picked up in the immense detectors that dot the LHC. The patterns of these bursts leaving a signature hidden in the mess of possible outcomes in proton collisions. And so eventually, with enough time and enough collisions and cascading energy bursts, an unambiguous signal emerged out of the noise. The physicists held their breath as the significance climbed above 5 sigma, the threshold for scientific discovery. Enough to whisper, yes, this particle exists. Mass does not arise by magic alone. In no time at all, the God particle, as the Higgs boson was known, was everywhere. Even though this name is despised by the majority of the physics community, its origin a book written by Nobel Prize winner Leon Lederman, a title to drive up sales rather than please the sensibilities of physicists. Indeed, Lederman at one point even considered the nickname the goddamn particle instead. The media whirlwind made the discovery the biggest physics news of the year, but the announcement was too late for the 2012 Nobel Prize, as that decision had already been made, although everyone knew that the 2013 Nobel Prize was surely in the bag, and Peter Higgs would be in Stockholm. And so, all's well that ended well. More or less. For now, scientists knew the mass of the Higgs. They could therefore estimate the stability of the Higgs field by comparing the mass of the Higgs to the mass of the heaviest of the fermions, the top quark. And it turned out that the top quark is about 38% more massive than the Higgs boson. And that places us in a very tricky position. If the ratio was less than about 36%, the minimum of the Higgs field would be stable, and we would be safe from its decay tearing through the universe. If this ratio was greater than about 42%, the minimum of the Higgs field would be unstable. The Higgs field would have collapsed instantaneously at the birth of the cosmos. However, at 38%, the Higgs field is neither stable or unstable. Instead, it is metastable. It is stuck in its local minimum with the potential of transitioning to the true minimum. This means that in 2012 we discovered that the decay of the Higgs field hangs over the cosmos like the sword of Damocles, waiting to drop and bring the universe to an end. However, to finish on a more positive note, physicists have a few words of reassurance. There is still a lot of uncertainty in the theories, and so we're currently unsure of the true stability of the Higgs field. And also, the probability of the transition is very low, and so the decay will not occur until the universe is much, much older than today. Although having said this, the decay of the Higgs field is really just a question of probability. And, like all games of chance, even rare events can happen. Perhaps, at some point in the universe, at some point in the past, the decay of the Higgs field began and is roaring towards us at the speed of light. In the words of Sidney Coleman, one could always draw stoic comfort from the possibility that perhaps in the course of time the new vacuum would sustain, if not life as we know it, at least some structures capable of knowing joy. This possibility has now been eliminated. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave us a comment to tell us what you think. Thanks for watching, and we'll see you next time.